Look closely at a modern silicon wafer. Thousands of microscopic electrical pathways are packed into a space smaller than a fingernail to route data. At its core, a computer has one foundational requirement. The central processing unit, or CPU, must be able to communicate with a wide variety of external memory and peripheral devices to do any useful work. If you were engineering a computer from scratch, the most obvious approach would be to use point-to-point connections, giving every single device its own dedicated wire routed straight to the CPU. This illustrates the failure of that approach. Connecting the CPU directly to memory, graphics, network, keyboard, mouse, and sound cards requires dedicated pins for each. Scaling up creates an exponential explosion of wires. The processor runs out of edge space, creating an unmanufacturable, tangled mess. Direct, dedicated connections physically fail at scale. Building systems with dozens of interconnected components requires a different structural strategy for managing communication traffic. The engineering solution to this pin bottleneck is the computer bus. A bus is strictly defined as a collection of wires and protocols through which data is transmitted from a source device to its destinations. Look at this schematic. The defining characteristic is this single, thick purple line connecting sources to destinations. It's a shared transmission medium. This simplifies expansion. New devices simply tap into the central line without needing dedicated wires routed to the processor. But this design introduces an immediate engineering trade-off. Because the medium is shared, devices must take turns. They lose the ability to have concurrent, dedicated conversations with the CPU. The bus solves the physical space problem, but introduces a complex traffic management problem that requires strict protocols to govern who can speak and when. It is common to picture a system bus as a single wire, but a typical implementation consists of 50 to hundreds of separate microscopic lines. To maintain order and manage traffic, these hundreds of lines are strictly classified into three functional groups. The first group is the data lines. This is the bidirectional payload pathway used for moving the actual information between system modules. The number of lines here is referred to as the width of the data bus, usually 32, 64, or 128 bits. That width dictates how many bits can be transferred at a single time, serving as a hard limit on system throughput. Next are the address lines. This is a unidirectional routing pathway used to designate the exact destination or source of the data on the bus. The width of the address bus determines the maximum possible memory capacity the entire system can support. Finally, because the data and address pathways are shared by all components, the system relies on the control lines. This third group acts as the crucial arbitration mechanism, transmitting command and timing signals. High bandwidth and expanded memory capacity serve no purpose if the signals collide on the wire. The control lines act as the synchronized traffic lights of the system. Let's step through a practical example to see these three lines working in concert during a standard memory read operation. First, the CPU must send a target location down the address line. Simultaneously, the CPU transmits a specific memory read command down the control line to authorize the action. Only then does the memory module place the requested data onto the bidirectional data line to be received by the CPU. This high-speed sequence exposes the critical vulnerability of the shared medium architecture. What happens if two devices attempt this process at the exact same time? Look at this schematic of a central data bus. Every single line has multiple sources and destinations. If two devices transmit during the same time period, their electrical signals physically overlap on the wire, destroying the binary integrity, turning voltages into a garbled mess. The bus architecture only survives because those control lines enforce absolute turn-based arbitration over who is allowed to use the lines. While the single bus solves the pin problem, it creates a hard performance ceiling as computers grow more complex. This slide outlines physical limits of a single bus system. First, data transfer bandwidth is fixed. Adding components merely divides the pie into smaller slices. Second, propagation delay. More attached devices means a longer bus, taking signals longer to travel end-to-end. This creates a severe latency mismatch. A central processor operating at gigahertz speeds cannot pause and wait for a slow, mechanical hard drive to transmit data on a shared wire. A single, universal bus forces the fastest, most vital components to wait in the exact same traffic jam as the slowest ones. The solution is a tiered bus hierarchy. The top processor memory bus is a short, extremely fast connection dedicated to CPU and memory traffic. It evolves rapidly, abandoning backward compatibility. Lower-tier input-output buses branch via adapters to handle slower, diverse peripheral devices. These I/O buses evolve much more slowly because their primary constraint is maintaining backward compatibility with legacy hardware, like older peripheral component interconnect (PCI) expansion cards. By dividing the pathways, data traffic on the vital CPU to memory bus is massively reduced, physically isolated from the slow, varying latencies of external I/O tasks. Modern computer architecture doesn't eliminate the shared medium bottleneck, it quarantines it. This tiered approach allows engineers to deliver both cutting-edge processing speed and versatile component expandability inside the exact same machine.